Hey everyone, and welcome to another deep dive. Today we're going to be looking at Chapter 12,
Atoms.
Atoms, from your Class 12 Physics textbook.
That's right.
And big shout out to,
To India's insert.
yes, India's Insert for making these freely available.
Absolutely.
So you as a high school student can follow along with us
Yeah,
and, get a better understanding of this stuff.
that's the goal.
Yeah. And get this, we're talking atomic structure.
It's going to be exciting.
We're going to figure out how scientists figure out what atoms are really like.
And it's a long story.
Plot twists.
Yeah, it really is. It's
Yeah.
like a detective story. Scientists, even back in the 19th century, were convinced that atoms existed, even though they couldn't see them directly.
Right, they had evidence, but
They had clues
yeah.
based on how elements behaved, but no clear picture.
It's like they were working with a blurry photograph
Yeah,
of a suspect.
exactly. And one of the early models that was proposed was called the plum pudding model.
Plum pudding model.
By J.J. Thomson. And imagine this. Imagine a positively charged, sphere with these negatively charged electrons just embedded in it.
Okay.
Kind of like raisins in a cake.
Okay, I can sort of visualize that.
Yeah, so that's the plum pudding model.
But how do they go from plum pudding to something more, I guess, scientifically accurate?
Well, light was the key.
Okay.
Light was the key. Scientists started studying the light that was emitted by gases, and they noticed that when they heated gases, they didn't emit just a rainbow of light,
Yeah.
but very specific colors.
Oh.
Each element, think of it this way, had its own unique color fingerprint.
Okay, so these colors were what, like hints at the internal structure?
Precisely. They were like secret codes
Yeah.
telling us about what was going on inside the atom.
Yeah, yeah.
And then comes along Ernest Rutherford in
Ah.
1911.
This is a big name.
This is a big name, with his famous gold foil experiment,
Okay.
where he was essentially shooting these tiny positively charged bullets
What?
called alpha particles
Okay.
at a very thin sheet of gold foil.
So like a microscopic shooting range or
Yeah,
something.
you got it.
Oh.
Now, if the plum pudding model was right,
Yeah.
all of these bullets, these alpha particles, would pass right through with only slight deflection.
Right, like passing through, I don't know.
Yeah, like fog.
Like fog, exactly.
Yeah.
But here's the big shocker.
Okay.
Some of those alpha particles bounced straight back.
Bounce back.
Bounced straight back. Can you imagine that?
That's wild.
It was completely unexpected.
So not like bullets going through fog at all?
No.
Okay.
It would be like if you threw a tennis ball
Yeah.
at a tissue paper
Yeah.
and it bounced right back at you.
Okay, so that's not what they were expecting.
No,
Come
not
on.
at all. And this was a game changer for you, the aspiring physicist, because it really overturned the plum pudding model
Okay.
and led to what's known as Rutherford's nuclear model.
Okay, the nuclear model.
Yeah.
So no more plum pudding.
No more plum pudding.
Okay.
We're on to something new.
The nuclear model. And this is the picture you need to have. There's a tiny, dense, positively charged nucleus at the center of the atom.
Right.
And it's surrounded by this vast, empty space
Okay.
where the electrons orbit
Kind of like
closely.
planets
It's like planets around the sun.
around the sun.
Yeah.
Exactly. Now, there's a huge difference in scale between the nucleus and the rest of the atom.
Yeah, there is, right?
I mean, it's mind-blowing.
Yeah.
Your textbook gives a really vivid example. It says if the nucleus were the size of a marble, the atom would be as big as a football stadium.
Oh, wow.
So think about that. It's mostly empty space.
Okay, so I'm getting a better visual now.
Good.
Yeah.
Good. It's important to have that visual.
But even though it's this big step forward, the nuclear model,
Yeah?
I'm guessing it wasn't perfect.
You are sharp. You're absolutely right. Because according to classical physics, you see,
Yeah.
those orbiting electrons should constantly be losing energy
Okay.
and spiraling into the nucleus,
Right.
which would make atoms unstable. Yeah, and we're all still here.
Exactly. So something was missing.
So what was missing?
Well, that's where Niels Bohr comes in.
Ah,
Niels Bohr with his groundbreaking quantum model.
quantum. Now, this is where things start to get a little bit more complicated.
This is where physics gets really interesting.
Okay, so Bohr comes in,
He comes in.
and he's got a solution to this instability problem.
He does. Bohr combined classical physics with these revolutionary quantum concepts, and he made three postulates, or three kind of main points. First,
Yeah.
he said that electrons can exist in stable orbits without radiating energy.
Okay.
Second, those orbits aren't random, they're quantized,
Quantize.
meaning only certain orbits with specific energy levels are allowed.
So not like planets can orbit at any distance from the sun.
Exactly.
Yeah.
Exactly.
Uh-huh.
Electrons have assigned parking spots, if you will.
Okay, assigned parking spot.
And third, when electrons jump between those parking spots, they emit or absorb light.
Okay, so that explains
Those colors.
the specific colors that we talked about.
Exactly. Exactly. Bohr's model actually predicted the energy levels of the hydrogen atom perfectly and matched those distinct spectral lines that we were talking about. So this concept of quantized energy levels, it's really important for you because it explains, for example, how lasers work.
Lasers.
Lasers.
Pretty cool.
Which is, let's be honest, pretty cool.
Yeah. So Bohr's model?
Yeah.
It was a win.
It was a big step forward.
But was this the final word on the atom?
Yeah.
Or is there more to the story?
You're absolutely right. There's always more to discover.
Yeah.
And Bohr's model, as great as it was, had limitations. Right. Especially when it came to atoms with more than one electron.
Right, because now they're interacting with each other.
Exactly. Exactly. It gets a lot more complex.
Yeah.
To really understand those multi-electron atoms, we need another hero. His name is Louis de Broglie.
Oh, de Broglie. Okay, so that's where we're going next.
That's where we're headed, and that's where things get even more mind-bending.
Okay. All right. Another plot twist coming up.
Oh, yeah.
I'm excited. All right, well, we'll be back in a flash, so don't go anywhere. Okay, so de Broglie, he's the guy who said that electrons act like particles and waves, right?
Yeah, wave-particle duality.
It's one of those things in physics that you just, like, I don't know.
Yeah, you got
to wrap your head around it. It's hard.
It is. It's kind of a mind-bending concept.
It is. It's mind-bending.
But it was a really important piece of the puzzle because Bohr's model, as good as it was, worked great for hydrogen, but it started to break down when you looked at atoms that had more than one electron.
Right, because now you've got all these electrons interacting with each other, not just the nucleus.
Exactly. It's a lot more complicated.
It's like adding more balls to a billiards table, right?
Exactly. And so what de Broglie did was he provided a physical reason for why electrons can only occupy certain orbits.
Okay.
And this is a key idea, something that you'll see reflected in all modern atomic models. So his idea was that those parking spots that Bohr talked about could be explained if you think of electrons as waves.
Okay.
Think of it like a guitar string, right?
Yeah.
You can only play certain notes on a guitar string.
Right.
And those notes correspond to standing waves that fit perfectly along the length of that string.
Okay, so the electron is kind of like a
vibrating string.
Like a vibrating string.
And only certain vibrations or wavelengths or orbits are allowed.
Okay, that's kind of a cool way to visualize it.
Yeah, it's a nice analogy.
It is.
And it also helps explain why Bohr's model worked so well for hydrogen.
Okay.
Because hydrogen is kind of like our single string instrument, right?
Yeah.
It's got one electron. But when you start getting to atoms with more electrons, it's like trying to play a whole symphony on that one string.
Right.
It just doesn't quite capture the complexity.
Yeah, you need some kind of
a more complex,
more sophisticated theory.
Right. And that's where
quantum mechanics comes in.
Quantum mechanics, like going from a single string to a whole orchestra.
Exactly.
Yeah.
Exactly. So quantum mechanics embraces this wave-particle duality.
Okay.
And it gives us this more probabilistic view of the atom.
Probabilistic.
Yeah, so it's not about these electrons orbiting in these neat little circular paths anymore. It's about the probability.
So we don't know exactly where the electron is.
Right. It's more about the likelihood of finding an electron in a particular region.
Okay.
And these regions, we call them orbitals.
Orbitals.
And they have different shapes depending on the energy level. It's like saying, okay, there's a high chance the electron is somewhere in this cloud.
Yeah.
But we can't pinpoint its exact location at any given time.
So that's a lot more complicated than the orbits, those little,
It is. It is definitely more complicated than those neat little orbits in Bohr's model.
Yeah. But it's also more accurate. It's a much more powerful theory. And it allows us to do things like model the behavior of these multi-electron atoms and explain things that Bohr's model couldn't.
Okay, like what?
Like the intensities of the spectral lines.
Right, those unique colors.
Exactly. Remember those fingerprint colors?
A fingerprint, yeah.
Yeah. So quantum mechanics can tell us not only what colors are emitted, but also how bright those colors are.
Okay.
So it gives us even more information about the structure of the atom.
Yeah, so it's like we're getting a higher definition picture now.
Exactly. It's like upgrading our cameras.
Yeah.
And getting a much clearer view.
Okay, I like that.
So quantum mechanics really gave us a deeper, more nuanced understanding of the atom.
Okay.
And it revolutionized physics and chemistry.
Okay, so this is big stuff.
Yeah, absolutely. This is big stuff.
Yeah. Before we go too deep into quantum mechanics, I kind of want to go back to the gold foil experiment.
Rutherford's experiment.
Yeah, because I feel like we kind of glossed over it a little bit.
Yeah.
But it was huge, right?
It was monumental.
Yeah.
It was a turning point in our understanding of the atom.
So what made it so special?
Well, for one thing, it was brilliantly simple. You know, he took this existing idea, the plum pudding model, and he put it to a very direct test.
Right. Like, if this is true, then this should happen.
Exactly.
And then the opposite happened.
The opposite happened,
Yeah.
and the results were undeniable.
Right.
It forced scientists to abandon that old model
Yeah.
and start fresh. And it wasn't just about proving someone wrong. It was about uncovering a fundamental truth about nature. That the atom is mostly empty space with this tiny, incredibly dense nucleus at the center.
So it's like discovering a new continent or something.
It is. It's like you have to redraw the map
Yeah.
of the atom.
Yeah.
It was a complete paradigm shift,
okay.
and it had implications far beyond just the atom itself, right?
Okay, like what?
I mean, it paved the way for nuclear physics,
Okay.
which has led to advancements in medicine and energy production. I mean, it even shapes our understanding of how the universe began.
So this one experiment, like, had ripple effects through all these different areas of science.
Absolutely. It really speaks to the power of a well-designed experiment.
Yeah.
And also just the willingness to challenge existing ideas.
Right.
You know, Rutherford's experiment showed us that even the most fundamental concepts, the things that we think we know for sure, can be overturned when we have strong evidence to the contrary.
That's a good lesson.
It is. It's about being open to new evidence. And being willing to change your mind.
So we've got these incredible discoveries.
Yeah.
And we've got these models that revolutionized how we think about the atom.
We've come a long way.
We have, yeah. But what if, and this is just like a what if question.
Right.
What if Bohr hadn't made that leap?
That is a fascinating question.
Yeah, would we have gotten to quantum mechanics?
That's hard to say for sure.
Yeah.
You know, science has a way of finding its way.
Right.
But it might have taken a lot longer.
Yeah. Who knows, right?
It might have taken a lot longer.
Yeah. Sometimes it takes that one brilliant mind
Yeah.
to see the connections that others are missing.
Yeah.
And to really push the boundaries of knowledge.
So Bohr was a big deal.
Bohr was a game changer. Definitely.
Yeah.
Absolutely.
And then de Broglie came along and was like, hold my beer, we're doing wave-particle duality now.
Yeah, de Broglie was like, let's take it up a notch.
Exactly.
Yeah, it was an incredible period of discovery and innovation.
Yeah.
And it really shows the collaborative nature of science.
Right.
And just the power of human curiosity.
Okay, so before we go, like full quantum,
Yeah.
I want to touch on one more thing.
Okay.
Because we keep mentioning spectral lines.
Yeah.
These unique color fingerprints of each element.
How did scientists actually use this to study atoms?
Ah, you're talking about spectroscopy.
Spectroscopy, okay.
Atomic spectroscopy.
Okay.
It's a super powerful tool that we use to look at the light
Okay.
that matter emits or absorbs to
Yeah.
figure out what it's made of.
So, like, if I shine a light on something.
Well, it's a little more nuanced than that.
Okay.
You've got the basic idea.
Great.
We can take a sample of material,
Yeah.
heat it up, or excite it with electricity,
Okay.
and then look very carefully at the light that's emitted.
Okay.
And each element will have its own unique set of spectral lines, like a barcode.
So, like, if I point this spectrometer at a piece of iron,
Yeah,
I'll get a certain pattern of colors that's just for iron.
precisely. Precisely. And it's not just iron.
Okay.
We can use spectroscopy to identify all sorts of different elements,
Okay.
even tiny, tiny trace amounts.
So, like, if I found a rock on Mars,
Yeah.
I could use a spectrometer to see what it's made of.
Exactly. It's an incredible tool. It's used in astronomy, in chemistry, in material science, all sorts of fields.
Okay.
It's a way of seeing the invisible world of atoms and molecules.
So we've gone from plum pudding to planetary models to quantized orbits to electron clouds.
We have.
It's been a journey.
Yeah, we've covered A lot of ground.
Yeah. And we haven't even gotten to the really weird stuff yet.
Yeah, we're just getting started.
Okay.
The atom is a universe unto itself.
Yeah.
Full of mysteries and wonder.
I'm still trying to wrap my head around the fact that we can use light to analyze what stuff is made of.
It's pretty amazing, right?
Yeah, it really is. But how does it actually work? It's like those electrons are sending us these coded messages with their colors, right?
It is kind of like that. Remember we talked about how electrons can jump between those quantized energy levels?
Yeah, those parking spots.
Exactly.
And when they fall back down, they release a photon of light.
Yeah.
And that gives us those spectral lines.
Exactly. So let's say you've got a sample of some material, you don't even know what it is. You heat it up, which gives those electrons energy to jump to those higher levels.
Okay, yeah.
And then when they fall back down,
Mm.
they emit those photons, those little packets of light of very specific colors.
So it's like each element has its own light show based on how its electrons are arranged.
That's a great way to put it. Each element has its own signature pattern of spectral lines.
It's like a fingerprint.
Exactly.
So wait, are you telling me we can look at the light from a distant star
Yeah,
and figure out what it's made of?
absolutely. That's one of the most powerful applications of atomic spectroscopy.
Really?
Astronomers use it all the time
Oh.
to study the composition of stars, nebulae, even distant galaxies.
No way.
Yeah, it's how we know what the sun is made of,
Hmm.
even though obviously we can't go there and take samples.
So we're looking back in time, essentially.
We are.
Wow. And it all comes down to like these basic principles we've been talking about.
Exactly.
Quantized energy levels, those transitions, and those unique spectral fingerprints.
It all ties together.
It really makes you realize how everything is connected, like the smallest atom
I know, it's
to
amazing.
the biggest star.
Yeah, from the micro to the macro.
It's incredible.
It's one of the things that makes science so fascinating.
So we've come a long way on this deep dive, from those plum pudding models to quantum mechanics and electron clouds.
Yeah, we've covered a lot of ground.
We've seen how scientists have been chipping away at this mystery of the atom for over a century.
Yeah, and it's a journey that's still going on.
That's right. There's always more to learn.
Absolutely. Every new discovery just leads to more questions.
Well, on that note, I think we've given everyone a lot to think about today.
I think so too.
Thanks for joining us on this deep dive into the atom.
It's been a pleasure.
And remember, the next time you look at anything at all,
Yeah,
remember that beneath the surface, there's a whole universe of atoms.
a whole universe in every little thing.
And each one of those atoms is a story
It is.
of the incredible complexity and beauty of our universe.
So keep exploring, keep asking questions.
Yeah. And never lose that sense of wonder.
Exactly.